All right, welcome back. We're going to talk about 10.7 inscribed and circumscribed polygons. First off, some vocabulary I think you might already know. Inscribed is an inscribed polygon is a polygon with all its vertices on the circle. So this figure on the left, this is an inscribed polygon. Every vertex is on the circle. Inscribed means inside. The polygon is inside the circle. Circumscribed, a polygon is circumscribed about a circle if all its sides are tangent to the circle. Keyword there is tangent, right? So on the right here, we have a polygon outside of a circle, and each side is tangent to that circle. So this is a circumscribed polygon. This is an inscribed polygon. Inscribed means inside. The polygon is inside the circle. We have a theorem. If a quadrilateral is inscribed in a circle, then the opposite angles are supplementary. Now let's think about the proof of this. Take a look at angle ADC down here, vertex D, right? Its intercepted arc is arc ABC. Okay, so arc ABC is going to be twice the measure of angle D. Then take a look at its opposite angle. That would be angle ABC. Angle ABC's intercepted arc is arc CDA. Okay, now, so we have arc ABC and arc CDA. What would happen if you add those two arc measures together? You would get 360, right? Because ABC and CDA, that takes you all the way around the circle. 360 degrees is what you would get if you add those two arcs together. Now, we know that angle ABC is going to be half of its intercepted arc. And we know that arc ADC is going to be half of its intercepted arc. So while we don't know the individual arc measures, we do know their sum. And we don't know these individual inscribed angle measures, but we do know that when you add them together, it's going to have to be exactly half of the sum of their intercepted arc. So half of 360 is 180. So in a quadrilateral, I should say if a quadrilateral is inscribed in a circle, then the opposite angles are supplementary. So that takes us to example one. I'm going to fix these angle symbols here for you in your notes. But quadrilateral ABCD is inscribed in a circle. If angle A is equal to 110 degrees and angle B is equal to 95 degrees, find the measures of angle C and angle D. Pause the video now. Try this one on your own. Okay, angle A and angle C, they are opposite angles in a quadrilateral that is inscribed in a circle. So A and C have to be supplementary. So the measure of angle C is 180 minus the measure of angle A, which is 110. So the measure of angle C equals 70 degrees. B and D, they are opposite each other. They are opposite angles in a quadrilateral that is inscribed in a circle, so they are supplementary. The measure of angle D is equal to 180 minus the measure of angle B, which is 95, and we get 85 degrees for the measure of angle D. Try example 2 on your own. It's kind of fun. Inscribe a parallelogram in the circle below. Do this in pencil. Actually, I guess if you're using your computer, then it would be in a erasable digital pen, but try to inscribe a parallelogram in the circle below. If you try to inscribe your typical parallelogram, that is like a rectangle that's been tilted, right? Something like this, you will always end up with one vertex that is not on the circle. So your parallelogram cannot be like your traditional parallelogram that is like a tilted rectangle. So it has to be some other type of parallelogram. And I'm going to start by drawing opposite sides that are parallel to each other. All right, we end up with what appears to be a rectangle. You could have also drawn a square, and of course a square is a rectangle. So that takes us down to this next question here. What kind of parallelogram does your drawing appear to be? And it appears to be a rectangle. Let's think about this. Compare this to what we just learned about. So scroll up here, right here. Theorem, if a quadrilateral is inscribed in a circle, then the opposite angles are supplementary. So think about a parallelogram where the opposite angles are supplementary. It has to be a rectangle. So there's no other parallelogram where the opposite angles are supplementary. So there you go. That's kind of the proof of that. It's kind of tying that theorem into inscribing a parallelogram into a circle. And this leads us to our next theorem. If a parallelogram is inscribed in a circle, then the parallelogram is a rectangle. Now remember, a square is also a rectangle, so it could be a square too. Example 3, parallelogram ABCD is inscribed in circle O. If AB equals 24 and BC equals 10, find the area of circle O. I want you to think logically about this. You don't have to actually draw it, but think logically about this. Pause the video now and work this example. If the parallelogram is inscribed in the circle, what shape does it have to be? It has to be a rectangle. How do we find the area of a rectangle? Length times width. So if I told you you have a rectangle with two sides, 24 and 10, find the area of that rectangle, all you would do is multiply the length times the width, 24 times 10. And as I reread the problem, I realize now, yes, we do have to draw it. So I read it originally, find the area of the rectangle. I don't know why, but you have to actually find the area of the circle. So if you're here and you're stuck, draw the area of the rectangle doesn't help you actually. So anyway, draw the circle, sorry about that, and draw the rectangle inscribed in it. Use the information given to find the area of the circle. Think about what you need for the area of the circle. All right, sorry about that, guys. All right, so I drew my parallelogram inscribed in the circle. It's a rectangle. Think about how our center is going to divide the sides of this rectangle. It's going to bisect them, right? So you got a longer side and a shorter side, 24 and 10. So I'm going to draw in half the shorter side, which is going to be 5. And half the longer side is going to be 12. And this is important because to find the area of the circle, I need my radius. So there is my radius, r. We're going to have a right angle here with the horizontal portion and the vertical portion. So we have a right triangle, and pause the video now if you haven't already done so and find the radius of that circle. So we end up with a radius of 13. You could use the Pythagorean theorem, or you could have noticed you had a Pythagorean triple, 5, 12, 13. Either way, you get a radius of 3. Area of the circle is equal to pi r squared. Pi times 13 squared is 169 pi units squared. Were we asked to round here? No, we were not asked to round, so we're going to leave it in terms of pi. We don't know our units, so I'll just write unit squared. I would not be a stickler for this part. If you left off unit squared, I wouldn't be bothered by that. But if we were given the units like inches or feet or whatever, I do need to see your units squared there. I really like this next theorem. It's pretty cool. If a quadrilateral is circumscribed about a circle, then the sum of one pair of opposite sides is equal to the sum of the other pair of the opposite sides. So we're going to find the sum of this side and its opposite side and compare that to the sum of the other two opposite sides. So you don't have A, B, C, and D written on your notes. This is a proof for why this works. You actually don't even need the links here, but if you wanted to look at the links, this was done in, I believe, Geometry Sketchpad. Anyway, the point is we have tangent. So we have tangent lines here. And if you recall, the tangent lines are going to be congruent to each other. So from vertex S, we have these two segments from that angle to the point of tangency. They're going to be congruent to each other. Same thing here. From vertex R to the point of tangency, these two segments are going to be congruent to each other. Same thing C and C, same thing D and D. This is also kind of the foundation for a walk-around problem as well. So as we find the sums of the two opposite sides, I'll do the top and bottom first. So this top side is D plus C, and the bottom side is A plus B. And that's going to be equal to the sum of the other two opposite sides, which is going to be D plus A and C plus B. So D plus C plus A plus B is equal to D plus A plus C plus B. We have one D, we have one A on either side, I should say. We have one C on either side, we have one B on either side. So there you go. If a quadrilateral is circumscribed about a circle, then the sum of one pair of opposite sides is equal to the sum of the other pair of opposite sides. Try example 4 on your own. Given the picture below, JU is equal to 18, UM is equal to 22, and MP is equal to 23. Find the length of JP. Pause the video now and try this one. All right, so we know the opposite sides, their sums are going to be congruent to each other, or equal to each other. So 18 plus 23 is equal to 22 plus x. You see that here, 22 plus x. So x is going to be the length of JP. We solve for x and we get 19 equals x, so JP equals 19. Last example, try this one on your own. We have the measure of angle A, angle B, angle C, and angle D. We're asked to find the measure of arc BAD. Pause the video now, try this one on your own. All right, so if you'll recall that when we have a quadrilateral that is inscribed in a circle, the opposite angles are going to be supplementary. So A and C are supplementary, B and D are supplementary, and you see all that work over here on the left side for that relationship. And we end up with a system of equations, two unknowns, 9x plus 2y equals 166, 8x plus 4y equals 192. I'm going to take this top equation, multiply it by 2, and I'm going to use elimination. It's a lot easier than substitution in this problem. So when I multiply the top equation by 2, we get 18x plus 4y equals 332. And we subtract from that the bottom equation, 8x plus 4y equals 192. We end up with 10x equals 140. Divide by 10, x equals 14. Now, to solve for y, we have to plug x equals 14 into an equation that has both x and y in it. I'm going to plug it in here, 9x plus 2y equals 166, but any of these equations would work that have x and y in them. And when I do that, I get y equals 20. So 9 times 14 plus 2y equals 166, y equals 20. Now we're asked to find the measure of arc BAD. BAD. That is the intercepted arc of angle BCD, or you can call it angle C if you want to. So if we find the measure of angle C, we can then find the measure of its intercepted arc. Let's do that now. And we find out that the measure of angle C is equal to 82 degrees. So if inscribed angle C has a measure of 82 degrees, its intercepted arc BAD, must be twice that, which is 164 degrees. All right, thank you very much for sticking with me. Make sure you get all your work done, do your best, all that great stuff. See you in class next time.